not member do a presentation, but I do have previous experience in the Philips cyber football team. And actually I see lots of people I recognized from my period at Philips within our current team. So yeah, our team experience also goes a long way back actually. About myself, I'm an electrical engineer. Officially I graduated in Delft University in 1988. And after that I did 20 years of software development at several companies, until the love between Philips and me ended, and now I work as an independent entrepreneur in language and technology. So I'm in a new field really. I guess the team has great expectations about my participation because I am the only team member with a private office, so you will see that tomorrow. So. Progress in our team within the last year. I don't know. Is there really so much new? I think not. And also, if I look at the various robots in the MSL League, well, with the exception of Tech United, I was very impressed by the robot with arms. It will probably play basketball as well. But most of the MSL robots look very similar. They look like Daleks. I don't know if you guys know the Daleks. I guess it also says something about my age. The Daleks were from the Doctor Who television series, the great antagonist of the Doctor himself, and they were actually invented by the science fiction writer Terry Nation, and they already appeared in 1963 in the television series. So yeah, they look like Daleks really. So I heard there are teams that do not have their own robot with them, and then I have some good news. Of course, it's something the doctor might have said. The best view of Dalek is the exploded view. It looks about like this, and from this you can construct your very own Dalek, like the little one I've shown you. And I have one for each team, so you can build your own robot if you have come without one. You can make that with only a very sharp knife, they say. I've cheated myself, I've used some glue, but all you need is a very sharp knife to assemble this. Since 1963, that's 51 years of progress, and how far did we get in this time? If you look at the peripherals, for instance, the Daleks were equipped with suction cups, which are not allowed in middle-sized league. They also had the laser gun. We cannot use that, and they had one single eye. I think we have improvement on that side. I think all the teams use OmniVision at the moment. Right, all of you. Okay, so there's improvement on that area. So let's look at our robot. What it looks like. The OmniVision is at the top, of course. We have a welded aluminum frame, very well-known ball handler that's also used by other teams. Kicking device that can kick along the floor and make, that's correct, a lock. And there's almost standard 3 omnidirectional wheels. And also, I will come into that in a moment. A foolproof battery charging system. I have actually managed to plug that one in the wrong way, and that did not destroy the batteries, so it's truly foolproof. So you have hardware and you have software. Well, we don't see very much of the hardware team because stuff just works, and we have a lot of activity on software because there's problems there. But the hardware is very stable, very robust. And one point I would like to talk a little more about in the hardware is the battery system, because there is a very old saying in electronics, any machine is as good as its power supply. I like to fix broken machines as a hobby, and very often, I think 50% of the time, you will find a problem in the power supply. Well, okay, here is an example of a machine, and I think that one is powered by dilithium crystals, which are very rare in our section of the universe. So dilithium was not an option, but of course lithium batteries are quite popular nowadays, and we do use lithium. As a matter of fact, we use lithium iron batteries, very good battery type, but unpopular at the moment because it is accused of causing a fire in an airplane. So there are all sorts of restrictions on exporting these batteries, for no good reason at all. Anyway, we have our own supplier right here in Eindhoven at the Kanaldijk. So, and we have a very good relationship with them. As a matter of fact, they will create a custom designed battery for us that exactly fits the frame of our robot. So that's, even better hardware. So one of the special things about it is that it has a charge control that works per cell. A battery, the name already says it, consists of several cells, and when your battery is broken, there's only one cell that is giving you trouble. So what you need to do for good battery maintenance is per cell charge control. That's all implemented in our system, in these batteries, and that gives you the foolproof performance I was speaking about already. So, hardware has no problems. How will we win? Yeah, the cleverness will have to be in software, of course. Our design approach is KISS design. I don't know if that's a familiar term for you. KISS stands for keep it simple, stupid. So we are going for the most simple solution because it's the most robust usually. For instance, there's of course a lot of data in the system, and it has to be communicated between several modules. It's simply stored on a blackboard, a large area of memory where any module can drop its data and other module can pick it out. Very simplistic model. Also the software, the modules, are small tasks, as simple as possible, and there's a scheduling to have each module have its own turn to use execution time. No preemption, no interrupts, no difficult stuff, just round-robin scheduling, and of course each module has to voluntarily give the CPU to the next one. So there's also no concurrency between modules. There can be no doubt whether somebody else is maybe writing in your data area, except for the vision process, but that's another story. coordination is by a finite state machine, and this is controlled by what we call the statics engine. Statics is a sort of a programming language which has, of course, states and transitions between them. The states we call action skills. There are actions like stand still, move to ball, turn around, simple actions like that. And decision skills take care of the transitions between these states. Currently we are, as I told you, very hard work on the software, mainly on the path planner and the path smoother, and cooperation between robots. Yeah, well, we are already very glad if we get one robot to perform in the right way at the moment. So team planner, we have ideas about it, but it's still in the future. So we are mainly working with path planner and path smoother at the moment. So let's focus on the difficult bit then. The path planner, if we go a long way back, about 12 years back, the Philips cyber football team already had a path planner, of course. Everybody has. You have to go somewhere. As Johan Cruyff once said, I hate it when people are moving and don't know what their target is. So you have to know where you are going. Long ago we had potential field, only in the surroundings, the direct surroundings of the robot, the vicinity of the robot. And later on we started with the potential field covering the whole field, but of course the larger your field gets, the more you have to calculate. As a matter of fact, it increases quadratically with field size, so that becomes difficult, and even then the potential field only gave very simple behavior. So yeah, you calculate about the whole field, but most of the field is empty. If you look at the size of the robots and the ball, it's only a very small area and a very large field. Most of it is empty. So the new planner only looks at interesting areas, the goals, the opponents, our own robots, ball, of course, and now also has enough time to take the velocities of the objects into account, and it only produces a rough path, so step, 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 and then the smoother comes along and makes a nice fluent path out of that. And then when the path has been calculated, we hand it to our finite states machine, and we activate the follow path skill, and it simply has to follow the points calculated. Now the path planner itself, there's one team member who's very active with that, and I'm not quite sure he's still using the KISS approach actually. It's quite complex, and what he told me about it is this. So he's working with the visibility graph, which is already also quite aged system, because it was already used on Shaky the robot, the first general purpose mobile robot that could reason about its own actions back in 1969. Now I hate it when people look at their sheets and not at the audience, but I cannot remember it. A visibility graph is a graph of intervisible locations or set of points and obstacles in a Euclidean plane. Okay, Euclidean plane, keep that in mind, I will come to that later. Each node represents a point location, and each edge represents a connection between them. Okay, a visible connection. Good. That is, if the line segment connecting two locations does not pass through any obstacle, an edge is drawn between them in the graph. Okay. To me, this does not tell which edge you will be following, but maybe it's beyond me, this path planner business. I know we are working very hard on it, and we desperate need of Jurgen van Eyck, who is implementing this, and he will be there tomorrow, so then you can maybe get the knowledge from him directly. Euclidean plane, yeah, flat surface, that's right. We live in flatland, maybe you have heard about that, about the two-dimensional world where people only knew two dimensions, and they, like we cannot imagine a fourth dimension, people in flatland can only think in two dimensions. They have no idea of z coordinates. Our coordinates are x, y, and rz.